Okay, right away. So back here with the session. Settlement is always something that engineers should know, especially structural engineers. But say even though you don't plan to work on structural engineering, but the time may come when you need to do some, modification to your house, because many people would love that, to extend the kitchen out back, and the problem always occurs with this, because we especially live in Bangkok, where we have a special soil condition, and so oops. So we need to understand when we are dealing with that kind of problem. So generally, I have brought the issue of the settlement into the example is because we live in Bangkok, where we have a special kind of soil condition. It's called Bangkok clay. You cannot build anything on clay. But we Thai people have done that before. For example, because clay is just basically something, just like a jelly. So in the past, they can increase the bearing capacity of the clay by, putting the shallow foundation as many as possible, piles, so that, the soil condition improve. It's still a shallow foundation because in the old days, they would use the wooden piles that no more than maybe a few meters long. Okay. Nowadays, they still have the hexagonal pile. You may have seen that before. Okay. The ones that they use to build the fence or the walls around the house, stuff like that. This is also very short. The longest one, maybe they put like two pieces of them together to create like 6 meter pile, but still that is still considered shallow foundation. So when we have shallow foundation like this, what we do is we improve the soil condition so that the area underneath can take more load and you can build maybe a house on it. But technically, this house will not sit on a solid foundation. It just floats on clay. But this clay has been made strong enough by a series of piles driven into it. I have a house like this. It's been built like 50, 60 years ago that sits on the shallow foundation, wooden piles like this. And you know what happened? At the back of my house, there used to be a water pond like this, but this is a soil. And when you have a water pond with the soil like this, you suppose the water would come in like this. The water level in the ground would be something like this. And then one day, because this is my house, and then we have a wall here, so that the guy who owned this pool, they decided to make it into a concrete pool. So they make this a solid pool. So that means the water level in the ground disappeared. So when water goes away, the soil condition here changes. So I have a problem with the house because when the water is gone, the clay here loses its strength. So some of the piles at the back of the house goes down. So I got a settlement problem, and generally, if you have a settlement problem, you can jack up the house and reconstruct your foundation. But this house is so old. In fact, the entire house sits on the shallow foundation. So there's no way to jack it up. So, it's very, very funny to talk about this because we have a structural engineer in the house, and then we have settlement problem that the structural engineer cannot do anything about it. So we have to let it rot. And it's very funny because this is used to be my bedroom with 2 kids, and you know, the settlement is so visible, you know, and the doors became stuck, couldn't open the door because the rotation is so visible. Yet we still live in it, but now we got a new house, so we're happy. Now, in general, for typical, say, construction, a typical house now in Bangkok or anything, let's make it like a 2-story house, whatever. They don't do this anymore because we have the technology. So the foundation has been a deep foundation nowadays. Okay, so that the weight of the house is sent to a more solid datum line. Generally, this is about minus 21 meters from ground level in Bangkok. This is where we find the first solid level that we can drive the pile down here and let the piles sit on this solid ground. It's I don't know what it's called because I'm not the soil mechanics guy. Never was, never am, never will be. But this is what we do nowadays. So it's completely different animal to this. Now our structure sits firmly on the firm soil level. So when you guys want to build your little kitchen, maybe here, generally the area will be limited. So what many people would do when they want their house expanded, they would build this on the ground right away, sometimes without foundation, sometimes with shallow foundation. And what they always do is that they will attach this new structure to the house. So imagining this one is sitting on nothing and your house is sitting on the deep foundation. So this entire new thing can pull the house down entirely because the house is not designed to hang on to something like this. So this is the common and general mistakes made every day in, you know, small villages that they don't care about anything. They sell villages to you, they sell a house to you, and then you move in and you in the end you think it's too small, you want to increase the area, so you know, expand your house, may I add, illegally, and then you add something like this to the house, and this is not supposed to be supported by the house. So even with the tiny things like this, it doesn't sit on any foundation, or it sits on the clay, just like this one. And mind you, this is the clay without any soil improvement. And this tiny thing can drag the whole house down. So when you want to have your house expanded, it is absolutely important that you know that you cannot connect the new structure to the existing one because of the problem with the foundation. Cannot connect the new one to the existing one. Now the next question that comes in should be, what if the new structure have foundation as well? Let's say you do it properly, we're gonna have the same foundation like this. Can I connect them together? The answer is still no. Not even new structure is on proper foundation, because they are built at two separate times, so they have different settlements as well. So whenever you join the structure without necessary and without the proper knowledge on this aspect, you will ruin your career. And in fact, this is kind of a very typical question they ask when you want to level up your license, you know. You must know this. Okay? So, is there any question? And I can draw you another picture just to show you that the typical problem that we have. Like, for example, this is your huge Wisawa Watana building, for example, right? And then they will always build the stairs. And then sometimes I don't want to put these stairs on the structure of the building. I just want to lay it on the ground. So this one is on deep foundation, right? This guy is on the ground, so this guy sinks first. So you see the crack between the stairs and the buildings. It's only usual. It's only normal. And if you paid attention, you would have seen it before, right? Any questions, guys? Hello? Are you with me? Hello? No question. So let's move on to the next problem. Okay. No question, right? Okay, fine. So let's move on to the next example. Now we are going to deal with this thing, and it is something that you must know and must be able to take advantage of. Let's take a look at this problem. Okay, you see, even with the slope deflection equation, the very powerful method to solve it, it is always nice to recognize the fact that, let's say this is A, B, C, D, E. Now the structure is symmetric. Well, when it is symmetric, it means that you have the line of symmetry like this. And when you have a symmetric structure, it means that both the structure and the loading condition must be symmetric. Okay, so in this case, we have a symmetric structure, even though this is a hinge, this is a roller, but we ignore the axial deformation, remember? We shouldn't have a problem with that. Okay, so it can be considered symmetric. And when the structure is symmetric, that is something that you can tell right away. And not only that, when we face this problem, you know, in this case, we know that when we have a support like this, moment at C must always be equal to 0. So when you have a structure like this, you know that here your MA must be 0. Do you agree with me or not? It can't be anything else, right? Because this is what we call, this is a simple support at the end of your indeterminate structure. So we call this a simple end support. So when we have this situation, we know right away that MA is equal to 0. So it seems a bit silly to try to set up the equation MA be equal to 0 and try to solve it. And likewise, we know that ME here is 0 as well because it is a simple end support. Okay, before I proceed with this one, I kind of recall that we have the previous issue with this one. Right, so excuse me. Could we go back to this example? Remember example number 4. Okay, and then to try to facilitate this, I will go back to example number 3. Okay, guys, it's cleaner. So are you with me? Are you with example number 3 now? Now.
Yes.
Okay, thank you for your response. Much appreciated. Now, in this problem, we can sort of identify degree of freedom that you need to solve. So I'm going to have this kind of question to measure whether or not you can identify your unknowns in the exam. So you need to make a statement, the degree of freedom of the structure need to be solved in general. And in this case, let's say if I have A, B, C, and D, you know, the statement, the first statement is that degree of freedom of the structure need to be solved. That would be zeta B and zeta C, right? You know your zeta A and zeta D are 0. So you know the value, you don't need to solve them. So in general, the unknown that you need to solve is zeta A and zeta B. So move on to the second one. When you can take advantage of symmetry, you now know that this structure is symmetric, correct? Because the same length, same moment of inertia, and same loading. Now, the line of symmetry is right in the middle of the second member. So when you are going to have a symmetric structure, it would mean that, you know, the deflected shape should be symmetric, right? So this is negative curvature, this is negative curvature, and that, and that. So when you have a curvature that looks like this, look at zeta B. Let's use different color. Zeta B is clockwise. And if this picture is going to be the same, symmetric, I mean, how would zeta C be related to zeta B? If this is a symmetric picture, now, you know, most of you will go ahead, okay, the rotation must be the same, but look more carefully. Symmetric, it means it's like a mirror image. You can fold the two together about its own line of symmetry, correct? So if you can fold these two pictures to become one about this axis, zeta C must be in this direction. So for this case, it means that if you realize that the problem is symmetry, you will know that zeta B is equal to minus zeta C. Correct? Otherwise, it's not symmetric. So when taking advantage of symmetry, it means that we are 2 degrees of freedom here becomes 1 degree of freedom, because you know that zeta B is equal to minus zeta C. So let's come back to this example. Now, I like I told you the first time we solved this one, I want to carry out the whole thing and solve everything for you. In fact, I could begin by saying that zeta C is equal to minus zeta B from the beginning. Let's try to use different color. Zeta C is equal to minus zeta B, and I can sort of plug it in here. Oops. Sorry. So in fact, this problem can become one unknown and one equation, because you now know that zeta C is equal to minus zeta B. So you only need one equation, because these two equations become the same. So one equation, then gone. So when you have symmetry and you can take advantage of that, it means that your work will be reduced for at least like 50%. So I strongly encourage all of you to feel the structure, feel the symmetry, and try to always take advantage of the situation. Because first of all, good engineers can work smart and can work very quickly and correctly. By taking advantage of symmetry, you reduce your work. You work more quickly. And with reduced work, you are less likely to make mistakes. And more quickly, save more energy. You can spend your energy doing something else. That's the first reason. The second is that, this is not symmetry. The second is that a structure like this is very, very common. When you design continuous beams, you know, in RC, in steel design, it's just so common that you have symmetric structure like this. And good experienced engineers can design, you know, a beam like this, say, in less than 5 minutes. And I'm not saying this to discourage you. I'm saying this to inspire you that one day you should be able to design things like this in 5 minutes. You know, you are in front of the construction and somebody want to change the beam and you just, hey, wait a minute, let me recalculate, and you do it in 5 minutes. How cool is that? Imagine someone who doesn't understand the behavior of the structure. Oh, can I go back to my office and turn on the program so that I can analyze the structure accurately by using a computer? And then they mess up the input and then got the wrong answers and so and so. Okay? If being an engineer is all about using the computer program, you know, my kids can be engineers now because they can turn on computers, they can use programs, they can use applications. There's no point for you guys to study anything, right? Engineers are much more than using computers. Okay. Now I should try to talk about this as well. A simple end support, because we can take advantage of one more thing. The fact that when you have a simple end support, you know that the moment here is 0. So there is no need to try to solve it. Okay. So you guys can, oh, that's okay. I don't need to go back there to the PowerPoint to try to solve it. If I can find something here. One moment, please. Okay, it's right here. All right. So let's say I can use this. Okay. Ooh. Let's say we have our structure. This is continuous, and we are now focused on this support. Remember, it has to be the end support, and it has to be either the hinge or the roller. So this is called simple end support. See, that word comes first. It has to be support at the end, and it has to be simple support. Many students got confused with this, and I feel kind of sorry when they want to do this and they mess it up. It has to be end support. It has to be a simple support. Okay, let's call this one I. This one J. We can write our slope deflection equation Mij 2ek 2 zeta I plus zeta j, and let's include this psi term as well, minus psi ij plus femij, and then you have mji 2ek 2 zeta j plus zeta I minus psi ij, and then plus FEMJI. Now I already know that my MIJ is 0. This is 0. So I can take advantage of knowing this value, and I will try to eliminate zeta I by using these two equations. So I can just multiply the second equation, the second one, multiply this by 2, and then I can, let's say this, okay, 2mji minus mij. If I do this, I can eliminate zeta I, and therefore I have mji. Remember, we don't need mij because we know it's 0. By doing this, we have mji equals 3ek zeta j minus psi ij plus FEMJI minus FEMIJ over 2. So this is the modification that when you use this, you don't have to bother count for zeta I. And you don't have to do anything to calculate MIJ because you know MIJ is 0. Right? Now, it's a sad thing that I think, I don't know what to do this, but let me try to remind you guys that because MJI and MIJ generally, they don't share the same sign, right? Because you know, when you calculate your fixed end moment, MIJ is generally counterclockwise, which is negative, and then MJI, it's generally clockwise, which is positive. So when you use this equation, some students, you know, especially folks who are here for the second time, you mess this up, and you know it. Because you don't take care of your sign very well, right? It's sad, and you need to be aware of things like this before you graduate and become true engineers. So when FEMJI in this case is positive and FEMIJ is negative, so it's negative against negative, it becomes positive, but not always. But you should always pay attention to the sign. And when you pay attention to the sign now, you will see that, in fact, this equation gives you a very good shortcut, you know. And I always give this equation in the exam. You can flip the page, look at the back, and take the right one, because from time to time, there will be folks who, okay, you know, multiply 3 again, multiply this by 2, multiply this by whatever. All kinds of silly mistakes trying to use the equation, trying to work as true engineer, but you are too careless. Okay? So we have another powerful equation that you should always use, but make sure that you know how to use it. Okay, and this will help reduce the number of unknowns you need to solve even further. All right, so let's go back to, oops, no, not this one, sorry, my mistake. Let's go back to this. and scroll back to problem number 2. Take forever to get there. Oh, not it. 3, I'm sorry, not 2. Okay, so when you look at this problem and you try to make a statement, we don't have a simple end support in this first case, correct? So no simple end support because your end supports are fixed. So when taking advantage of symmetry, you can reduce your unknowns from 2 to 1 because you know that your zeta b is equal to minus zeta c. But for simple end support, there's no simple end. So it remains 1 degree of freedom. Now take a look at this one. Now we have support A, B, C, D, and E. Okay, so that means in general, your unknowns are 1, 2, 3, 4, 5, right? Zeta A, zeta B, zeta C, zeta D, and zeta E. So in general, you have 5 degrees of freedom. So let's say you are very confident of your slow deflection equation knowledge, but you're not so confident about your modification. You will have to solve this structure by, coming up with 5 equilibrium equations. Not nice, okay? But again, okay, my instructor says something about symmetry. So that means I know that my structure will deform like this, perhaps. This is a simple end, so the rotation comes out like this right away, and then the negative moment here, and then perhaps positive, and then comes back to here. So because the loading condition is symmetric and the structure is symmetric, right? So from this, we can say that like the same, zeta B is equal to minus zeta D, right? Because if they are going to be symmetric, it's just like the problem above, zeta B will go this way and zeta D will have to go the opposite way, so that you have a symmetric structure. But one more thing that you should know, because if it is going to be truly symmetric, what do you think is going to occur to zeta C? What do you think? If you are going to have symmetric structure, what is going to happen to zeta C?
0.
Absolutely correct. That's the only way that this beam will behave with symmetry in mind. So zeta C is 0. So that means if we take advantage of symmetry, we can reduce 2 more unknowns, right? So one more thing I forgot. That is zeta A is also equal to minus zeta E, right? So 1, 2, 3. So now you have 2 degrees of freedom left. That is A and B. But wait a minute. We have simple end support as well, right? A is end support and it is also a simple support. So that means you already know that MA is 0 and likewise for ME because it's symmetric. So if you use your modified equation that I just showed you, it means that you don't need to solve for zeta A. How about that? Do you like that? So that means simple end support you can eliminate zeta A. Eliminate it. Zeta A is not 0. Zeta A is not 0, but it can be eliminated. So by taking advantage of simple n, plus symmetry, you are down to 1 degree of freedom that you need to solve. See, from 5 to 1. From 5 equations to 1 equation. What's not to like about it? Right? Questions? Before the question, let me go back here and point one thing to you. If you don't like to use this equation very much, if you so hate it for some reason, you can always set these two equations up and while doing the analysis, proceed to eliminate Mij first. It's the same thing. You can do that as well. Okay? Is there any question? Piece of cake, right? Wow, you never thought that structural analysis, it's this easy, you know? Yeah, actually, I can make your life easy or I can make your life difficult. It's up to me, really. But honestly, I don't see a point to make this extremely difficult anymore because chances are you may use computer more often than hand calculation, but you need to understand the behavior of the structure first. And the beauty of slope deflection is that it allows you to see it. And sometimes if you want to get on with a simple structure, it is a lot easier than to use the computer and then try to create the model, put a load on it, and so on. So, you know, it's a quick, efficient when you have, you know, a symmetric structure like that. Very, very quick. Okay, so if you don't have any question, let's try to work our way with this example. Okay, so now you know that this is typical, it's just like that. So if I am going to use everything, so I have only, let me write everything down for you. The unknowns. Step number 0, the unknowns are zeta A, zeta B, zeta C, zeta D, and then zeta E. And then, you know, I think some of you may have a way to mess step number 0 up very badly. And it makes my job very difficult when I try to grade your work. And I think you don't do it intentionally in a way, but intentionally in another way, which actually you mess it up because you don't have a clear picture on what you are doing. That's why you mess it up. So generally, if this is the case, you can say zeta A is, you know, eliminated because we can take advantage of a simple n support, and zeta E, you know, simple n. Zeta C is 0 because of symmetry. And then zeta B is equal to minus zeta B. So we're good to go, right? I don't have any number to work. It doesn't matter. So step number, what's step number 1? Oh, okay. Step number 1, relative stiffness. So you now have KAB is equal to I over L. KBC is 4I over L. So let's say my K is equal to I over, well, L. So my KAB is therefore K, and my KBC is 4K, right? Simple enough. And because I don't have any number with me, and if I ask some number from you, it may take forever. So let's just say FEMs. FEM AB is going to be equal to FEM BC equal to FEM CD equal to FEM DE. That's not it. Equal to minus FEM BA equal to minus FEM CB equal to minus FEM DC equal to minus FEM ED, and this is of course WL square over 12. All right. So step number 3 now, slope deflection equation. So when I realize that I'm going to take advantage of the fact that support A is simple n to eliminate the need to solve zeta A, I am now obliged to write MBA with the modified equation. Correct? Now, where is my equation? Right. Is it? Need to look for it. I may remember it, but just to make sure that no mistake is made. Okay. This screen, wrong screen. 3K, just K, right? Because that's member AB. Zeta B minus psi AB, which is 0. And then plus MBA, which is WL square over 12, right? Minus FEMAB, which is in fact minus of this, minus WL square over 12. And don't forget that we have to divide this by 2. So that is by MBA. And, you know, let's say, because I just make things up, I don't have anything with me, so I may make a mistake. If that's the case, please remind me as well. 3ek zeta b plus, that becomes WL squared over 8, right? You have 112 plus 124, right? So it's 224, 324 becomes WL squared over 8. So that's your MBA. And then I can go on and write my MBC. MBC is a typical span now. So the typical equation, 2e 4k, remember? 2 zeta b plus zeta c minus psi ab. This term is 0. That is 0. And then you will realize that MBC is minus WL squared over 12. Okay, so here we are. Because we have only one unknown, we can proceed to step number 4 to construct equilibrium equation, which is, sigma MB equal to 0, that is MBA plus MBC is 0. So, you know, one equation, one unknown, your zeta b will come out in no time. I forgot to complete this, so that's 16 ek zeta b minus that term. Okay, equal. So in fact, we have 19 ek, oops, sorry. ek zeta b, so that's 8 and 12, that's 24 again, 324. So that means plus WL squared over 24 equal to 0. How do you like that? One equation, one unknown. So you're done, right? So now you must realize the fact that you don't have any other equations. So how do you solve others? You need to write, you know, other necessary equations to get your end moments. Okay. So if you want MAB is 0, right? No need to do that. Silly. MBA, you already have that equation. Okay. MBC, you already have the equation. That. What about MCB? Many would think that MCB is 0, but no. You can calculate this by, you know, writing the equation. 4k and then zeta b, right? Plus WL squared over 12. That's MCB. And voila, your job is done. So it's not, again, I say that word a lot and I'm beginning to hate it, but it's true that it's not rocket science to take advantage of symmetry and simple n. If you do that, it helps reduce your work dramatically and it helps reduce your error as well. And you see, I can be tricky at times, so I always give a problem like this. So you have one of the two ways to tackle it. The first is try to understand the behavior of the structure, take advantage of everything, that is available to you to take advantage of, or simply go head on into the problem and try to solve 5 unknowns, which if you get it right, you may feel silly in the end. If you get it wrong, if you get zeta b not equal to minus zeta d, for example, if you get MA and ME not equal to 0, for example, you should know that fatal mistakes have been made somewhere. Okay, so that's it for example number 7. Is there any question? Question? No question, I suppose. No question. You want me to move anywhere? You guys are taking photo of something? Should I stop here? Or should I stop here? Okay, if there isn't any question, it's time to take another break, I suppose. It's been exactly 50 minutes. Question? Okay, there isn't any questions, so I'm gonna stop the chat. And I am gonna stop the record for a while.